Hello, George Romanic here. Today is a big day for this channel as well as for you. Today I will share with you geostrophic approximation and geostrophic wind equations. One of the most fundamental concepts in synoptic meteorology and dynamics of motion of air at large scales. Some atmospheric science videos out there introduce meteorology and atmospheric sciences by first talking about geostrophic wind. And they are doing it wrong. Yes, I am bashing some other content creators. But I feel pretty good about it, to be honest. Why are they doing it wrong? Well, while geostrophic approximation that you will see today is very simple concept, balance between horizontal pressure gradient force and horizontal Coriolis force. To get to that concept, you need to overcome many hurdles. And we did it proper way. It took me more than a year to introduce different concepts that when understood properly can lead to geostrophic approximation. Namely, what I mean by that? Well, to properly understand geostrophic approximation, I believe you first need to understand forces that are affecting parcel of air, in terms of real forces as well as apparent forces. Then you need to know what is material derivative in inertial and non-inertial reference frames. Then you need to know how to put all these forces as well as advective terms in something that we call Navier-Stokes equations. And then you need to know how to perform scaling of Navier-Stokes equations in the horizontal direction for the phenomena of large-scale motions in mid-latitudes. And then you will see what we saw in the last video, that the magnitudes of various terms in Navier-Stokes equations are such that for synoptic scales in mid-latitudes, the two forcing terms that dominate the motions are pressure gradient force in horizontal direction and Coriolis force in horizontal direction. That's the proper way to arrive at geostrophic approximation. And we did it the proper way, and I congratulate you for staying with me for over a year to do it the right way. Now, let's go and examine geostrophic approximation. First of all, I hope you will not mind that I will use this part of the paper for today's lecture. I don't want to waste paper. And this is from one of my previous videos where we carried out scale analysis of the horizontal components of pressure gradient for mid-latitude cyclones, so it's somewhat relevant also for today's lecture. But today's lecture is on geostrophic winds, and to discuss that, the best is to start from our scaling table. This is scale analysis of the horizontal Navier-Stokes equations at synoptic scales in mid-latitudes, and we saw that the two dominant terms at these scales in mid-latitudes are the pressure gradient force and the horizontal component of the Coriolis force. So at the first order analysis, we can only retain these terms and we can neglect all other terms in Navier-Stokes equations. The balance between these two forces, balance between pressure gradient force and horizontal component of the Coriolis force, will give us geostrophic balance. So retaining only these two terms, notice that in the x direction we have 0 is equal, there is nothing on the left hand side, we have minus 1 over rho delta p delta x and plus f times v, where you will remember that f is Coriolis parameter 2 omega sine phi. Phi is latitude. In the y direction, there is nothing on the left-hand side, and we have minus 1 over rho delta p delta y minus f times u. And this, ladies and gentlemen, boys and girls, is the geostrophic balance. Now keep in mind that this geostrophic balance is diagnostic relationship. It gives approximate relationship between pressure field and horizontal velocity in large-scale extratropical systems. There is no time dependency in these equations, so we cannot use them to analyze how the system will evolve. We can only tell you how the system looks like right now. Whenever you give me pressure gradients and you give me latitude, I can give you how the geostrophic relationship will look like, but I cannot tell you how it will evolve with time. It's very important to understand that. We can define horizontal velocity field that obeys this relationship, and we call that geostrophic wind velocity. Namely, Vg as a vector is equal Ug in the I direction plus Vg in the J direction. And these are component of geostrophic wind in the west-east and south-north direction. Positive eastward, positive northward. So I can add subscript G over here because these are now geostrophic wind components. Of course, we can go always a little bit further and write this in vector form, and that would be Vg in vector form is equal K, which is unit vector in vertical direction, cross nabla P over rho times F. And this is the same as this, just in vector form. You can convince yourself by carrying out this cross product. I'm not going to do it here. It's very, very trivial. At any rate, if you want explicitly components of Ug and Vg, then you just express them from these equations. So you can see that Ug is negative 1 over rho f delta p delta y, and Vg is 1 over rho f delta p delta x. Namely, U geostrophic component is proportional to meridional pressure gradients, and V geostrophic component is proportional to zonal pressure gradients. You also have to keep in mind that this is mathematical model of the wind, because we neglected some of the terms that are less important, but nevertheless they do influence motion. So this is the mathematical concept of the wind if only these two forces exist. But this mathematical relationship approximates the real horizontal winds in the free atmosphere to within 10 to 15%. So it is very, very good approximation. Now let's look a little bit geometrically how these winds look like. Let's assume first we have purely meridional pressure gradient in the Northern Hemisphere. That would look like this. So here I would have pressure P, here I would have P minus delta P, let's say. This is my X direction, this is my Y direction. Keep in mind that this delta P difference has to be positive, so this is high pressure, this is low pressure. We have a parcel of air over here, and there is balance between pressure gradient force that acts from high to low pressure and Coriolis force that acts to the right of the wind vector, and this is Vg, wind vector, and in this case we can see it's purely zonal. We have only U component. Now let's look at purely zonal pressure gradient in Northern Hemisphere. So if we have pressure P here, let's say here is lower pressure, P minus delta P, where delta P is again positive. So this would be high pressure, and over here we have low pressure. Same coordinate system, we have a parcel of air, pressure gradient force is acting like this, pressure gradient force, Coriolis force is acting to the right of geostrophic wind Vg, which in this case only has V component, because pressure gradient is purely zonal. So this is Coriolis force. Now some of you might say, but wait a minute, how is this equilibrium being established? Because when the air starts moving from high pressure to low pressure, then Coriolis force starts acting. And that's an excellent question, but it's beyond the scope of this particular video, because remember, geostrophic relationship is diagnostics. We cannot tell anything in terms of time, how the system evolves in time. Remember that Vg from previous page was K cross delta P over rho F. There is no time here. Therefore, we can only apply this relationship when we already have established equilibrium between these two forces. We cannot use this relationship to see how the equilibrium evolves. Anyways, let's look into combined zonal and meridional pressure gradient. So let's say that would be C. So that would look like this something. And let's say again, this is P minus delta P. So this is high pressure and this is low pressure. We have a parcel of air here. We will have geostrophic wind like this. And now notice it has both UG and VG components in this coordinate system. Pressure gradient force is P, pressure gradient force PGF, and Coriolis force like this. You can also conclude now that in Northern Hemisphere, geostrophic wind blows in a way that high pressure is to the right of the wind and low pressure is to the left of wind vector. Let's see another case, let's call it D, where we have variable pressure gradient. Something like this, for example. And again, let's say this is P minus delta P. So this is high pressure, this is low pressure. How would geostrophic wind look like? Well, here it would be, let's say, like this. If this is the magnitude of geostrophic wind here at location 2, let's call, then here, if we have location 1, geostrophic wind would be weaker than here, because the gradient here is weaker than the gradient here, and geostrophic wind is proportional to pressure gradients. If the pressure gradient is large, that means small distance between P and P minus delta P, geostrophic wind is high. If the pressure gradient is small, which means big separation between isobars, geostrophic wind is weak. And again here, for example, at the exit, it would again be weak compared to point number 2. And lastly, let's not forget our friends in the Southern Hemisphere. So let's here provide an example of, let's say, I don't know, meridional pressure gradient in Southern Hemisphere. How would that look like? So we have this meridional pressure gradient. Let's say here is P minus delta P. So this is high pressure, here is low pressure. We have parcel of air. What will happen in this case? Well, it will move in this direction. Pressure gradient force still goes from high to low pressure, but remember, Coriolis force is reversed in Southern Hemisphere. It acts to the left of the motion, and therefore in Southern Hemisphere geostrophic wind will blow in a way that low pressure is to the right of the wind and high pressure is to the left. Here in the Northern Hemisphere we have opposite, high pressure to the right, low pressure to the left. At the end I would like to demonstrate how powerful this geostrophic approximation really is. Here I have a synoptic map above Canada, this is Canada, that I obtained for 12 January 2022 at 0 UTC or Zulu time. And I took it from Plymouth State Weather Center. In blue, these blue contours represent geopotential height in meters of 500 millibars pressure surface. So along each of these lines, we have 500 millibar pressure, and you can see above Canada on this day, 500 millibars was at approximately 5.3, 5.2, 5.1 kilometers above Earth's surface. For now, I would like you to concentrate on these regions where lines of constant geopotential are straight. Because when they are curved, we have to introduce centrifugal force, and that's what I will do a few videos from now, and we will get gradient wind balance. But here, where the lines are straight, there is no centrifugal force, and our geostrophic balance should hold. And indeed, it holds, because these brown barbs represent wind at 500 millibars, and kindly note how wind is almost perfectly parallel to the lines of constant geopotential. High values of geopotential mean high pressure underneath, and we said in Northern Hemisphere, geostrophic wind blows in a way that high pressure is to the right and low pressure is to the left of wind. And notice here you have that 5300 is to the right of these two wind vectors, wind barbs, and 5200 is to the left in respect to their direction of these winds. You can see that geostrophic approximation is so strong that it's difficult to find where we have deviation from geostrophic approximation. You can find it in certain regions. Here we have coastal region characterized by high mountains, inhomogeneity in terrain, and here we broke geostrophic approximation. To demonstrate that I am not cheating here, I obtained randomly different map. You can see this is map above Europe for 19 March 2014, 12:00 UTC. And it's also 500 millibar geopotential height. If we take this region over here, lines of constant geopotential are pretty straight. And you can see that this wind is parallel to these lines. And again, high pressure is to the right, low pressure is to the left from wind barbs, which you can think of as wind vectors. It's very difficult to find regions where this is not the case. Another beautiful demonstration on this synoptic map is look at this region over here. I told you, when pressure gradients are high, wind speed is high, and you can see that by the number of these wind barbs over here. As the pressure gradients get small, wind speed becomes small, and this is what you see here. And as pressure gradients again increase, wind is picking up as well. Pressure is constant along these lines, it's 500 millibar pressure. But different values of height of constant pressure also indicates different values of pressure gradient. I highly suggest you check my video on pressure as vertical coordinate. And soon we will also express geostrophic wind in a pressure coordinate system. There isn't much more to say about geostrophic approximation. We see it in a conceptual form, and I also showed you few simple examples that hopefully give you better physical feeling for this dynamical process. As I said, this is very important day for my channel. Geostrophic approximation is a big deal in atmospheric sciences. Unfortunately, I don't have whiskey at home because I'm out of it, and my local whiskey store is closed due to COVID-19. So I cannot celebrate with whiskey, but I have a beer. So I can celebrate with you using this beer. Cheers. Now you know geostrophic approximation. Go down the street and show off. It's almost as good as whiskey. But not quite. Until next video, goodbye.